Okay, this is Ksp relative solubilities, Ksp common ion, and Ksp precipitation. 15.6, 15.7. On the worksheets, do number 1, A, and B. Now, I had to kind of change question B a little bit, just some wording I left off that they use on the AP. So for B, do part, it says B1 and B2. You'll see I rephrase the question on it. Then number 2, do number 1 and 2 also, and then do number 4. And if you want to do other ones, you certainly could, but those are the main things that they ask about on the KSP problems. All right. Now, so what's the good news about this, 15.6, 15.7? Well, you might remember that I told you in Chapter 15. Chapter 15 is like the bonus stuff. Like, I want to make a 5 on the AP. Now, except Chapter 15 has KSP officially in it. So you need to know how to do KSP. We will see that later on a quiz or something, or at least on the test. So KSP is an important one. But if you can already do all the KA and KB from Chapter 14, and if you can do a KSP problem like the ones we had on the yesterday's assignment, the one before this, then you will be able to pass that question on the AP. If it's a KSP, a KA, KB, you can pass it. If you can do any of the problems from yesterday's assignment on the KSP worksheet, and any KA or KB that we had in Chapter 14. Okay, now, after you do the KA or the KB, after you pass the question, now I want to get to 4 or 5, that's when they're going to add in the stuff about buffer, like you saw in this Chapter 15. So buffers are like what comes beyond the ice box, find the pH, find the percent, and all that kind of stuff, find the OH, then the buffer comes. Well, KSP is the same way. After you do a KSP problem, then they add in this. Or sometimes they can add it in along with it, and you'll be able to just, if you can do a basic KSP problem, you should be in good shape. But I'm going to do all the types of problems here right now. So it'll be a bunch of different problems I'm going to work out for you. And not a lot of information. So the good thing is, it's just mostly a lot of math problems here. I guess that's good. Just a lot of math strategies, problem-solving strategies. Okay, so the first thing I'm going to do, it begins in 15.6, which we already started yesterday, or yesterday lesson, whatever you want to call it. And then we go, and if you notice after A, B, C, D, then there's a part that says relative solubilities of salts. This is something that is not really brought up on the AP very much. But I'll just tell you this one little rule. It says on letter A, arrange the following in groups of in order, and not groups. Arrange the following in order of decreasing solubility in water. They give you 3 KSP values. Well, unfortunately, you cannot just say decreasing solubility means from high solubility to low solubility, or lowest. Okay, and that means the smallest solubility would be that one, and that will be the greatest solubility and the lowest. Okay, here's what I'm going to say. I interrupted myself. Unfortunately, you can't just look at KSP values to find this out unless all of the molecules involved have the exact same positive to negative ion ratio. Well, not even that. If they have the same, that's even wrong. Well, that might be right, but the same number of ions total. I'll show you what I mean. Copper, CuS, copper has 1 copper and 1 sulfur ion. Oh, I'm sorry. I'm doing the wrong problem. I can't believe this. Copper is not the one. Letter A, arrange the following order of decreasing solubility. I read it right. That shows from high to low. That's decreasing. So, Ag and I, there's 1 positive Ag and 1 negative I. Copper plus copper 1 iodide. 1 copper positive and 1 I negative. Calcium sulfate, 1 calcium plus 2 and 1 sulfate negative 2. If they have 1 positive and 1 negative ion, all of them, you can look at their KSP values. And so the one that has the highest number, which is 1.6 10 to the negative, no, 6.1 10 to the negative 5, that will be the most soluble right there. So 1.6 10 to the negative 5 will be calcium sulfate. Then the least soluble will be the one that has the smallest number, AgI 1.5 10 to the negative 16. And then CuI will be in the middle with a 5 times 10 to the negative 12 Ksp. So you can only look at those numbers. That means more of it will dissolve in water, and that means very little will dissolve in water. You can only trust the Ksp value if you have the same number of ions in each formula, like one positive, one negative, one positive, one negative, one positive, one negative. Because if you don't, like on letter C, what if you don't have the same one positive, one negative, two positive, one negatives, or two positives and three negatives? What do you do then? Then you got to do an ice box and solve for X, the solubility. You got to do a long X box for them. X box, ice box. Okay, for all of them. Now, yes, they've required that, and I'm going to probably do one for you, and I'll have to jump through a lot of it. I'll try to go quick through it. Okay, so we'll get to that in a minute. So that's all you need to know about relative solubility. But now, here's one they do like to bring always on there. The common ion effect. Common ion effect, we did it with buffers, and now we're going to do it with Ksp, but it's a lot easier with Ksp. And so, I'm just going to read it off to you to the problem A. Well, I think I do. I think I want to do A. Oh no, A is just defined. Well, I'll read A. I'm not going to do A, but A says, for silver chromate, it says the Ksp equals 9.0 10 to the negative 12. And it says find the solubility in water. Well, we could do that. You just do the ice box, you find X. What is subtracted? That's easy. I'm not going to do that one. I'll do part 2. Part 2 says, okay, excess is added to this. What's the solubility in that? Okay, I tell you what. I'm going to rephrase this question because I kind of need to better coordinate my notes and what's on the AP and what's on your worksheet. I did it on your worksheet already. I'm going to do it for this problem. I'm going to change this question to say this. 100 moles of silver nitrate are added to a saturated Ag2CrO4 solution. What is the solubility of Ag2CrO4? This is a better way to phrase the question. Okay, 100 moles of that are added to 1 liter of a saturated solution, okay, of that. What's the solubility of silver chromate? Okay, so here's the point of this question. First, they would also ask you, probably write the equation for dissolving AgCrO4 in water, dissociation equation. And it's a solid, and so it's not going to dissolve very good. So maybe it will be the equilibrium. They'll probably say from the equilibrium system or something like that. You'll get 2 silver ions, and you get 1 chromate ion. And those are going to be aqueous. And we know the Ksp for that is 9.0 10 to the negative 12. Okay, so, all right. I'm just trying to save a little bit of time, but I skipped number 1, and it's the solubility in pure water. And if I had done number 1, this is all I would do. I would make an ice box, and I would just find X, like we did on the last worksheet. But now, here's what happens. In pure water, you start off, this is solid, and it's going to always be solid. Only a little bit will break off, right? That's pretty much always true for all KSPs. But in pure water, these would both be 0, 0, 0, and you solve for X. Well, this is not pure water. Even though, okay, you can assume that you haven't made the solution yet or whatever, or you assume you have the solution, but it says we're going to add 0.100 moles of silver nitrate. Can you see a common ion? Is there anything in silver nitrate that is also in silver chromate? Yes, silver. Okay, So you're going to have a concentration here. It's not going to be 0. That one will still be 0. In pure water, you'd start off with 0. You'd find the solubility of this. But now it's not pure water. You have a molarity. And it's going to be 0.100 moles in 1 liter. That makes it very easy. 0.100 moles. So Ag plus molarity is 0.100 moles divided by 1 liter. So that's 0.100 molar. Okay. So 0.100 molar is what you have in 1 liter. I think I do a worksheet like that too, and it's assumed if they just say 0.100 moles is added, it should be to 1 liter. They should say that. Now, if AP said you add 0.100 to 2 liters, well, then it will be 0.100 divided by 2, and that will be half of that. Okay, that makes sense. So always think it through. Don't just assume always that you know the number. Watch what it says. That's 1 liter. Okay, so all I'll tell you is it makes sense from Le Chatelier that this is going to block some of this from dissolving. I mean, in other words, it's not going to completely be able to dissolve because that's going to cause it to shift back that way a little bit. So it'll be a little bit less soluble. But anyway, here we go. So what I'm going to put here is plus x, not plus x. I said it, but I didn't write it. 2x. Remember, change always matches the stoichiometry. Minus 1x, plus 2x, and plus x. 0.100 plus 2x, and x goes right there. Okay, so now let's find, well, next thing is let's write the Ksp expression. Okay, so for this one, Ksp equals, and here's the reaction, Ag plus, and it has to be squared, times chromate to the first power. There's only one of those. You don't have to put the 1, you can if you want. The Ksp value was given 9.010 to the negative 12. The silver at equilibrium is 0.100 plus 2x. And it's going to have to be squared. And then the chromate at equilibrium will be just x, 1 power if you want to do that. All right, so we'll assume x is negligible. And anything you add, a plus 2x or minus, there's no minus, or it can be taken away. So 9.0 10 to the negative 12 equals 0.100. Don't forget it's squared times x. All right, now, let's see. 0.100 squared, I'll just go on and do that. 0.0100x. That squared times x becomes that. 0.0100x is 9.010 to the negative 12. So we're going to divide that out. So 9 times 10 to the negative 12 divided by 0.0100. 9 times 10 to the negative 10. That's really, really small. Molar. Now what did we just find? We found the solubility. And you know, I said it here, and I'll tell you the same thing with AP. If they're not going to say that on AP. They're going to say the solubility in, they'll put mole per liter or in gram per milliliter, gram per liter, something like that. But if they just put solubility, or if I put that on a test like I did here on the worksheet, you can just put molarity. That's fine. Mole per liter. You know, mole per liter. So that they normally, if they don't say anything, they put mole per liter. That's quicker. 9.0, 10 to the negative 10. Now, molar. That is your X. That's your solubility. Moles per liter. And I like to also put in the formula. Moles of Ag2CrO4. So this actually tells me 9.0, 10 to the negative 10. Look how small that is. Something like that. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. There it is. That's how many moles of this will dissolve in every 1 liter. Really, really small amount of stuff. Okay, so that's how you do it. So the point is, if they say add something, then that's what you do. You don't worry about adding it. You start from the very beginning and pretend that it was there at the very beginning, because it will give you the same final result. You know, I don't really have to do the next problem because it's done the same way. But I'll set it up. I might zip through it really quick if you want to see another one. I just realized that from doing it, I can save a little bit of time. Look at letter B. Yeah, letter B. Okay, a new problem. It says calculate the solubility of CaF2, and they give the Ksp 4 times 10 to the negative 11. What is the solubility of this? Again, in mole per liter. You know, I don't think I just wrote these. I think that I got these from another textbook, a different textbook, it should say in mole per liter. AP always says solubility in mole per liter or in gram per milliliter, like I did the other day, the last lesson. But we'll just do mole per liter, and it'd be faster anyway, but because they didn't ask. What's the solubility of CaF2 in 0.025 molar NaF solution? There's one thing I can mention that I forgot to say on the other one, but I've told you in the past. NaF. Okay, it's easy if it's NaF. If it had been AlF3 solution, then it would be a little bit different. Okay? If you had 0.025 AlF3, think about. I'll get to that in a minute. But we're not going to do that. We're going to do this one. Okay. So for the ice box, you'd write down calcium fluoride to give you calcium and fluoride, and 2 fluorides. Okay. And then you'd have the ice box, and so that's a solid, and it still has a solid before and after. But now the calcium, it will be 0 because we have nothing there, but we have a common ion of fluoride. And can you see it'll be 0.025 molar right there. So you're not doing it in pure water, you're doing it in that solution, aqueous solution of sodium fluoride. So that's all you would do, 0.025, and then you do the whole problem. So if it had been, if it were AlF3, can you see now? I'm gonna have my Al concentration is 0.025, but my F is going to be 0.025 times 3. It will be 0.075 for F. Negative. Can you see that? If it had been 0.025 AlF3, now the F will be 0.075 because you got to multiply times 3. 1 mole of this has 3 moles of fluoride. 1 mole of AlF3. But I didn't do that to you or anything on this problem. But AP can certainly do that. They certainly could get it, and I could do it. But anyways, just watch that. So here we go. Minus X. That'll. Oh yeah, that's plus X. That's plus 2X. So X 0.025 plus 2X. So really, it's pretty much the same thing we did a moment ago. So I don't want to. If you want to skip past it, you can, but or try it on your own and then jump past it and see if you get it right to test yourself. And I'll just do it real quick here. So Ksp is going to be calcium ion plus 2, times the fluoride, and it has to be squared. So 4.0, 10 to the negative 11 is Ksp, given. Calcium at equilibrium is X, and there's only one of them, so and fluoride is 0.025 plus 2X, so it's going to be squared. And assume X is negligible. Okay, I know you better write the word out. I know I write so messy, but I at least want to write the whole word out. Okay, 4.0, 10 to the negative 11 is approximately going to be X times 0.025 squared. Hey, how easy that makes the math now. I get to ignore that part. So this is a really easy one, isn't it? So it's just going to be, I'll just do it on my calculator. I think you can get the math there. 0.025 squared is 6.25 10 to the negative 4, and 4.0 divided by that. So just divide both sides by 0.025 squared, and that will be your answer. Looks like it's going to be 6.410 to the negative 8. I'll double check it. 4 times 10 to the negative 11 divided by 0.025, divided by 0.025 again. It's 6.410 to the negative 8, yeah. 6.4 10 to the negative 8 molar equals X. And of course, I want to make it, I like to write it down mole per liter moles of what? Moles of CaF2 will dissolve in every 1 liter of that solution. Okay. So, anyway, it's just like a Le Chatelier thing. It makes sense if you increase, remember Le Chatelier, if you're at equilibrium, if I were to increase the amount of fluoride, that takes it out of balance, so now it's going to have to shift to the left. And as it shifts to the left, it's going to make the calcium go down a little bit lower. And it's also going to make that go down lower. It will be less soluble. You know, that's the main thing. So it's less soluble when you add one of these things in there because it shifts it to the left. So you can just treat it from the very beginning as if you had it there. All right. On both problems. Okay. All right. So those are the two. Those are not too hard, are they? So if they ask it, they haven't asked KSP in a while. So if they were to ask KSP this year, and they asked that, like first they asked, what is it in water? Then they said, oh, what is it in 0.025 molar? That's a pretty easy one. But here's the ones that gets a little bit crazier. Here are the ones. All right, so B, we did B. There's no need to do C. I don't know why I put another one in there. I just was using different numbers in it. Okay, pH on salt solubility. I wouldn't worry about that one so much, except all you're going to do there is, in this case, if you know the pH, like you see magnesium hydroxide is there, then you can treat, like if you know the pH of a solution, you say, oh, now I'm going to put magnesium hydroxide in a solution with a pH of whatever. From the pH, you can find the POH. If you know the POH, you can put that in for the OH, a common ion. I don't know. It has long ago that was on AP. I think they once put them together. It's like combining acid and KSP. But what you would do is, all you do there, I actually give you a question here, so I'll have to make it up and just tell you. But it says, what would happen to the solubility if acid is added to a saturated magnesium hydroxide, and explain why? Well, the acid would actually be able to react with the magnesium hydroxide. Actually, it's kind of interesting. If the acid did not take all the solid away, then the solubility would end up being the same. If the acid just took away part of the solid, if you still had solid remaining, then it's still going to be the same solubility. If you add acid, it would react with this. But now, what I was thinking of, if base is added, okay, if you put it in a basic solution, then what's going to happen is you can find your new you can find your OH find the pH, the POH, find the OH negative if you're in a basic solution, and put that in for your original OH negative. This is just a little, you don't have to really don't worry about that bit there. Okay, here we go. Precipitation and qualitative analysis. So, long ago, we did problems like you see on 15.7, net ionic equation. Aqueous lead-2 nitrate and aqueous sodium iodide are mixed, and what do you produce? Okay? I'll tell you what, to make it a little shorter, I will do letter B. Let me do a different one here. Okay. What is that? Cerium? Cerium. Well, I don't even see that one very much. I'll do B in that case. I'll do B. I'll do B on the next page. This problem right here. It says, okay, I'm going to do what I showed you, what I skipped a moment ago too a little bit. Magnesium nitrate. Let's just say that aqueous magnesium nitrate is mixed with 150 of magnesium nitrate is mixed with 250 of sodium fluoride. Okay? Now, it says for MgF2, they give you the KSP value. 6.410 to the negative 9. I'm going to come back to that in a minute. Well, I can write it, but I'm going to probably erase it. First of all, when these two things react, this is like a net ionic equation. They could ask you this on the AP. Write the net ionic for this. Magnesium will go with fluoride, and sodium with nitrate. Now, for the net ionic, magnesium and 2 nitrates will give you sodium and fluoride. Now, normally, I would always tell you that would just break up because, all the fluorides are soluble. But now they're telling you something about this, that magnesium fluoride has a low solubility, okay? So they're telling you that this is going to be a solid, maybe. So I'm going to put MgF2, I'll talk about that in a minute, and I'll put Na plus and O3 minus. According to this problem, they're saying that you might get some magnesium fluoride produced. Now, the AP, what they're going to do is they're not going to try and trick you with that on the equation. They're going to give you something that's going to work, all right? So if I didn't make this together, then there'll be no reaction. But, okay, will there be a reaction? They're actually asking here. All right, so notice, you might make magnesium fluoride. Let me say in a minute why you might or might not make it. And so all of these will be canceled out, and the sodium. So magnesium plus fluoride give you magnesium fluoride. So here is what they're asking you in this problem. Will a precipitate is solid? Will a precipitate form? Will this form as a solid? Yes or no? Okay. I don't know if you first have to think about the equation, and now you can see why they gave you MgF2. If MgF2 forms, then this is what's going to be what occurs. Write a little ice box, and that means it'll be in equilibrium with solid MgF2 will be in equilibrium with 2 fluorides. And you put a little ice box there, okay? We don't really need the ice box, but I'm going to show you. Now, if I write the Ksp expression, it's going to be magnesium times fluoride, and I'm going to square that. All right, what I'm going to do here is I'm going to turn this into a different kind of a setup. Ksp is equal to this, and we know the number, it was given on the paper, 6.410 to the negative 9 for MgF2. Well, Q, remember Q? If you are or aren't at equilibrium, then Q is tells you where you are. Uh-oh, Q is back. So here's the rule, and this is what you'll like. I'm going to plug in. They gave you a bunch of stoichiometry numbers here, so I don't even need my ice box, okay? I once told you can always draw it and abandon it. I don't need the ice box, but instead what I'm going to do is I'm going to do some stoichiometry stuff and find out whether or not a precipitate solid will form. Will you even have an equilibrium system? And what I did is, well, what I'm doing right now, I didn't do it yet. 150 milliliters of magnesium nitrate. Okay, I have that. And I also have 250 milliliters of sodium fluoride. I want to get to how many moles of this I'm going to have. So I'm going to have, first I got to go from milliliter to liter. Now, I'm going to run out of space. I'm going to try to write small so it'll fit here. 1 liter is 1,000. I'm sorry, top. 1 liter divided by 1,000 milliliter. Then what I'm going to do is I'm going to put, remember mole to liter by using molarity. For magnesium nitrate, it's 1 times 10 to the negative 2 molar. So 1 liter is, I can write it that way, or I can write 0.001. 0.01. Well, I'll write the number down. 1.0, 10 to the negative 2 moles of MgNO3 2 per liter. The other one has 1.010 to the negative 1 moles of NaF per liter. Okay? So, now, again, the good news here is I've only got one mole. You know what? I'll go in and I'll squeeze this in and put this one step. This is an important step to think about. Mole to mole. Moles of magnesium plus 2. Mg plus 2. There is 1 mole of magnesium plus 2 in every 1 mole of MgNO3 2. So I don't have to worry about it. Like I always told you, if it had been Al, or well, not aluminum in this case, but if it had been more than 1 magnesium, you'd have to put that number there. But it's a 1-to-1. This is not needed in this problem, but I'm just doing it to be safe. 1 mole of NaF has in it 1 mole of F, negative. Okay, so let's get that math right there. 150 times 1 times 10 to the negative 2 divided by 1,000. It's 1.5, 10 to the negative 3, 1.50 actually, times 10 to the negative 3 moles of Mg plus 2. 250 times 1 times 10 to the negative 1 divided by 1,000 is 0.025. So I'll put 0.025 moles of F negative. Let me double check my math. And you can ask yourself, would they really ask this on the AP? Yes, they absolutely have. And I'm going to give you some review stuff for equilibrium before the AP. And you're going to be amazed. The hardest question they ever asked on the AP on KSP. And I think you had to do 4 ice boxes in that problem. Can you believe that? A, B, C, D, E, F. And I mean, if anybody could do all of that in that amount of time, of course they're going to make a 5. They probably could have missed one of the ice boxes and still gotten a 5 that year. It was so hard. Okay, so let me do the math. So 150 times 1 times 10 to the negative 2 divided by 1,000. Yes, 1.50 10 to the negative 3. That's correct. And 250 times 1 times 10 to the negative 1 divided by 1,000 is 0.025, and that's correct. Okay, what am I going to do with these two numbers? Now I'm going to go over to Q. Q is equal to, remember, molarity is mole per liter. So for magnesium, the moles are 1.50, 10 to the negative 3. But how many liters do we have? Okay, now you got to look at this. 150 plus 250 is 400 milliliters. And of course, you got to change 400 milliliters into liters. Let me go on and do it right here, I guess. Unless you want to do it up there too. Well, I'll do it in both places. 400 milliliters, divide by 1,000. It's going to be 0.400 liters because you're adding those together. All right, now you're adding those. Sorry. Okay, so 400. No, I'm sorry. If you want to, 150 plus 250 over 1,000. Isn't that crazy looking? But again, as I told you, this is the way they actually have it written on their AP formula sheet. They'll do it that way. Kind of weird. But you can do it that way too, and just put 0.400 on the bottom. And I guess for this one, they'll do the same thing, 0.025. I mean, now that you know it's 0.400, you can just put 0.400, but you can do the same thing. This is because this meets the requirement. AP says you must show work for every math step. And you're showing every step there. You can just put 0.400 right here because you already know that's how you got it. Don't forget to square it. Okay, so now we're going to calculate this. 1.50, 10 to the negative 3, divided by 0.400, 3.75, 10 to the negative 3, times, I'm taking a step here, 0.065, 0.625 squared. All right, so I'm going to square that number times 3.75, 10 to the negative 3, and I get 1.46, 10 to the negative 5 is Q. Now, how does Q compare to KSP? All right, KSP for this problem for MGF2, 6.4, 10 to the negative 9. So is Q equal to, greater than, or less than KSP? So the rule is, if Q is equal to KSP, precipitation will occur. there will be solid, there will be an equilibrium system. If Q is less than the Ksp, it will not precipitate. If Q is greater, and that's what true is here, Q is greater than Ksp, so precipitation will occur. In other words, solid MgF2 occurs. It forms. You can just say precipitation occurs. But anyway, that's it. Because this number is a greater number than this number. Q is greater than Ksp, so it will precipitate. Now, I did letter... What did I do right there? I don't even know. I did B. Didn't I? Yeah, I did B. I didn't do problem A that came before it. Yeah, I didn't do problem A that comes before that. Probably on A it didn't. It was a smaller number. But let me tell you, remember, it's the same way we talked about Q. Does Q need to shift or anything like that? Q is greater than that. You can actually think of it this way. Precipitation will occur. Because Q is not at equilibrium. When you mix them together, it's not at equilibrium. And so what's going to happen is it's going to have to shift to the left, right? Does that make sense? It's going to shift left. Since Q is greater, that means that these numbers have to both decrease, and that's going to increase. So Q is greater than the Ksp. These numbers are too big, so these are going to decrease, and they're going to shift that way, and they're going to make solid. See, this is a solid here. Now, the cool thing, which I did not do on this problem, was, what if I did a math problem and it was less than the Ksp? If it's less, then what that means is that there's not going to be any solid formed at all. Like, you're going to have like 0.00001, 0.0001, whatever it is. These will not even multiply. There's not even enough of this to make a solid amount. That'll just stay dissolved in water. And it will, it'll just be, it won't even match the maximum solubility. That's another way to think about it. If you found the solubility of this with X in water, then the solubility would be the solubility would be less than, I'm sorry, I don't know how to say it. If the solubility were, I'll make up a number that's not true, but if the solubility were 2 moles can dissolve in every 1 liter, it's like saying that the amount of chemical you have is only like 1 mole. So you don't even get to 2 moles. So all 1 will dissolve, 1.1 will dissolve, 1.2, 1.3, 1.9 will dissolve. But then at 2, now 2 will dissolve, but now 2.1, you put 2.1 in there, only 2 dissolves, and the other 0.1 is going to be a solid. Okay, so that's kind of what I'm getting at here. But just remember that a little bit. If Q is less than Ksp, no precipitation occurs. And that has happened on the AP, where they gave you where it was less than, Q was less than the Ksp. There was not even enough solid to shift it. And if there is no precipitation, also there's no equilibrium. So that's why you don't even have an equilibrium system. Okay, now for the finale. I think this is it. Okay, so 15.7 talks about selective precipitation. If you wanted to pause the video, you could, to come back in later. It's like the last problem that says, which will precipitate first? Okay, that's going to be a crazy one. So, oh, wait a minute. Selective is kind of a cool thing. This is kind of what's called qualitative analysis, which I'm not going to really go through as much here because okay, here, this is, I didn't want to do this. Okay, so selective precipitation. Look at letter B. It says this. A solution contains 1 times 10 to the negative 4 molar copper plus ion and 2 times 10 to the negative 3 lead. A source of iodine is gradually added. Which will precipitate first? Copper iodide or lead 2 iodide? Okay, this is the mega problem, one that I talked about. So here's what goes on. They're giving you 2 KSPs. So I'm going to write down 2 equations. Copper 1 iodide to give you copper 1 and iodide. And the ice box for that one. And then you also have lead 2 iodide And of course, that icebox will be Pb plus 2I negative. And we'll put ice there. So one has precipitation of Ksp value 5.3 10 to the negative 12. One is 1.4 10 to the negative 8. Remember I told you a moment ago, if it had been copper 2 iodide, like pretend it was CuI2 and PbI2, then you could look at the numbers and know that the one that is more soluble will have a higher value for the Ksp, and also it will precipitate. More of it will dissolve in water, so it will be more soluble, so it will precipitate last. Okay, but anyway, let's just see. But they don't do that. Instead, what they do here is they put it so that you have different number of ions. The only solution is you have to calculate the solubility of each one to know which one's gonna precipitate first. Well, the one that is less soluble in water will precipitate first, and then the one that is more soluble will precipitate last. Oh, I'm sorry. That is true. That is one way you could do the problem, by finding the solubility. But the other way, which they usually do, and it might be a little bit easier, is to find out what's the common ion they have there, the iodide. What is the iodide molarity when precipitation occurs in saturation and of each one? So what I'm going to do, I'm going to find out what the iodide molarity is when they precipitate. That's a better way to do it. So for CuI, it'll start off, we don't know the molarity here. Remember, there's solid, minus X, 0, 0. We'll say plus X, X, and X. But for this one, we've got, again, solid, minus X. But here it's going to be plus X and plus 2X. Okay. These are two different problems, but they're going to be related. Like, why am I doing all this work? Okay, so here is what goes on. And I'll go back over it and tell you in a minute the two methods you could use to solve this problem. But I'm gonna do the more common one that they really like more on the AP. For whatever reason, they like this one. All right, so what I'll do is I'm gonna put let's see, Ksp for CuI equals Cu plus 1 times I negative 1. And that value they give you is 5.3 10 to the negative 12 equals X times X. Now, let me see here. All you have to do here is just get the square root. That's an easy, that math problem is not too hard, is it? Yeah, I was almost thinking that's just too easy. All right, so there's not even a, yeah, so 5.3 divided by, get the square root. Get the square root of that. Well, that's equals X squared. X equals 2.3 10 to the negative 6 molar. Okay, so here's what it tells me. At equilibrium, iodine equals 2.3 10 to the negative 6 molar. I negative. Okay. Now, let me do the one for PbI2. So Ksp equals Pb plus 2. I am sorry I left that off of my equation. Times I negative, and square that. So that's going to be, oh, I didn't write the number down. 1.4 10 to the negative 8 equals X times 2X, like a Y, squared. So this is a little bit more fun. 1.4 10 to the negative 8 equals So that's 4x squared, 4x cubed. Now notice there's no need for assume x negligible in these because you're able to solve for x. So 4x cubed. Now, to do the math here, just double checking. 1.4 10 to the negative 8 divided by 4. You get the cube root. Remember the cube root, raise it to the 0.33333 power. What if you want me to write this down? Okay, then that raised to the point, well, just raise it to the 0.333 power. If you want to write a cube root like that, you can do that too. You can write it down a little 3 there. But raise it to the 0.333 power. 33333. And it's 1.5 times 10 to the negative 3